Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum warahmatullah. Welcome to the first lecture of week 7. So in the last week we have been discussing chapter number 20 of our course book, that was the sheet metal working processes. In the last week we had discussed the first type of the sheet metal working process, that is the sheet metal cutting, which includes shearing and blanking, and the last one was the punching. Then we moved towards the bending, which had of two types. We had edge bending and the V bending. Now in this week we will discuss the third type of the sheet metal working process, that is the sheet metal drawing operation, or what is also known as the deep drawing operation, just to differentiate with the bulk deformation process of drawing, that was the wire and the bar drawing. So let's start with the drawing operation. So what is the drawing operation? It's a sheet metal process that is used to make cup shaped, complex, curved or the concave parts. So initially we have a blank that is taken as a stock material, and that is placed over the die, which has certain opening here, and the stock or the blank is held by a blank holder exerting some force for the holding. Then a positive part or the movable part, that is known as a punch, it comes in and draws this blank into the die cavity to attain the shape of the die. So the common products that are made from the drawing operation are the beverage cans, which we use in our daily life, ammunition shells, some cooking pots and some similar shapes. So if we see the mechanics of the drawing operation, so if we closely observe this diagram, so we have a die of the blank, that is the diameter of the blank, that is known as the dB. We have the die of the punch, that is dP, and we have certain radii at the corner of the die cavity. So the die from its corner should be rounded at some radius, it shouldn't be a straight edge. Why is that? So if it is a straight edge at the corner of the dice, when the punch comes in and applies the force on the blank, instead of performing the drawing operation, it will start to perform the punching operation. It will simply poke a hole into the blank that we have fed. So that's why the die should be slightly curved at some radius from the corners to avoid the punching operation. And if the punching occurs in this way, it will be a bad kind of punching operation. Then we can see there's some blank holder here that are exerting some holding force, which we will see in the slides ahead how to calculate it, and it plays a vital role in the drawing operation. And there's some movement velocity of the punch and the force that is exerted by the punch itself. Then we can see there's some clearance between the punch and the die cavity, and as we know, in the previous operation we have the clearance as equals to ACT, but in the case of the sheet metal drawing, the clearance is equals to 10% greater than the stock thickness, like 1.1 of T. So let's suppose if the stock thickness is 10, so our clearance should be 11, right? So it's a 10% greater than the stock thickness, the thickness of the blank. Then the holding force that is used to hold the blank, and it should be carefully selected. So that is some general schematic for the drawing operation. While performing the drawing operation, there's a series of deformation processes, and there's a sequence of stress and strain that is produced in the blank while undergoing the drawing operation. So let's see how the stages of deformation takes place during this operation. So during the process of the drawing operation, there are multiple stages of deformation. As you can see here, we have the blank here and the punch and the die opening. So when the punch comes in contact with the die, the first kind of deformation that occurs in the blank, that is the sheet metal bending, although you can see similar to the sheet metal bending. You can see here the metal is being strained along the corner of the die along the radii of the die by a punch and with the help of the blank holder. So the first kind of deformation that metals undergo during the drawing operation, that is the sheet metal bending. So sheet is simply bent over the corner of the punch and corner of the radii. So it is bending at two edges. We have the bending at the corner of the die and the corner of the punch here, right? So the four corners, the first, second, the third and this fourth one, the blank is being strained, is being bended along these four corners. And the outside parameter, obviously this is the two-dimensional view, but originally it's kind of a large disk. This blank is the kind of large disk. So the outside parameter of the blank move in toward the center of the stage. So this whole outside parameter is moving in towards the center of the cup that is being drawn like this. So the punch is pressing it downwards like this one. Now the second kind of deformation that takes place after this bending is like straightening, that is known as the straightening. Right. So the material which has been bended along the corner of the die, it when the punch moves downward, although the material at the bottom of the punch and along the corner of the punch remains there, but the material that is along the corner of the die, it straightens from this bended position. It straightens along the wall of the die cavity and forms the wall of the cylinder, and in doing so the material outside here in between the blank holder and the die, it moves or it flows or it is drawn into the die cavity. So so this is the additional material that comes in to replace the material that is being used in making the cylinder walls. So the new metal comes from the outside edge of the blank. So the metal in the outer portion of the blank is drawn here, as we have discussed earlier. During this stage of process, especially in this stage, the two additional factor comes into play. The first one is the friction, and second one is the compression. So during this stage of deformation, these two additional factors comes into play. So how do they affect this? In order for the material in the flange to move towards the die opening, the material in the flange means the material here, as you discussed, flange that is bended at the 90-degree. So in order for the material to the in the flange to move towards the die opening, friction between the sheet metal, our blank, and the blank holder and the die itself must be overcome. Obviously, if you want a smooth drawing operation, so the friction in between these interfaces of blank holder, the sheet metal and the die, these are three different surfaces, so this friction must be overcome. So initially when the material is stationary, so the static friction is involved. So once it has been overcome, the material starts to slide, then the dynamic friction comes into play and governs the process. So the magnitude of the holding force, sorry, so the magnitude of the holding force here applied with the blank holder, as well as the friction condition between these interfaces, they are the determining factor of the drawing operation. So in most of the drawing operation, we use lubricants in these surfaces for the smooth movement of outside material into the die cavity to reduce the friction forces. The second factor, that is compression, it is also occurring in the outer edge of the blank. So there's a compression that takes place in the outer edge of the blank, this outer edge of the blank, this one. As the metal in the portion of the blank is drawn toward the center, the outer perimeter becomes smaller. Why is that? So because when the metal is rapidly moving in towards the this die cavity or the die opening, the outer perimeter becomes smaller and it's become thinner. And because, as we know, the volume remains constant in this whole process, so the metal is squeezed and becomes thicker as the perimeter is reduced. So as we know, the volume is reduced as the volume is constant, So although with the reduction of parameter, the material becomes thicker and thicker, because obviously the volume remains constant throughout the whole process. So because this change in the parameter while maintaining the volume, the wrinkling occurs along the walls of the drawn cup. There's a defect that occurs that is called the wrinkles, or the wrinkling, that occurs in the along the walls of the drawn cup. So when the and this mostly occur when holding force is low. If FH is low, then the wrinkling occurs along the wall of the drawn cup. But if this holding force becomes too large, so there's a rapid thinning of the material along this die radii, and it might lead to tearing of the material. So this rapid thinning might lead to the tearing of the material, or the sheet metal. So determining the proper holding force involves a delicate balance between the multiple opposing forces, or the multiple opposing factors. So the progressive downward motion of the punch results in continuation of the metal flow caused by the drawing compression. So, and there is some thinning along the walls of the drawn cup during this process. As an empirical observation, when we perform the drawing operation, at least 25% of thinning takes place. During the drawing operation, the 25% of thinning takes place at the mostly near the base of the cup. Now let's move towards some engineering analysis of the drawing operation. The first and foremost, that is the drawing ratio. The drawing ratio that is used to determine the feasibility of the drawing operation. So the drawing ratio initially we can say it is equals to dB divided by dP. That is the die of the blank divided by the die of the punch. So drawing operation provides an indication, crude indication. If the drawing operation if the drawing ratio is greater than 2, so this drawing ratio it explains the severity of the drawing operation. If the greater the value of the drawing ratio, the more severe will be the drawing operation. So as an empirical observation, the upper limit of the drawing ratio is 2. So the drawing ratio, you can say in simple word, the drawing ratio should be less than equal to 2, right? So the blank can be at most twice as large as the punch diameter, right? So the actual limit value for the given operation depends upon punch and die corner radii, and the frictional condition between the multiple interfaces, the depth of the drawing that we are performing, and several other factors. So this depends upon, we can write it here, punch and die radii, punch and die corner radii. Then second one, frictional conditions, then the third one is the depth of the drawing. Depth of the drawing operation, and the properties of the material itself, you can write it this as well. Property of material, whatever material we are drawing. Then the second factor that is important while testing the feasibility of the drawing operation, that is the reduction ratio. So the reduction ratio, it is denoted by R. It is equals to the die of the blank minus die of the punch divided by the die of the blank. So it is somewhat similar to the drawing ratio. So as we know, the previous value for the drawing ratio, the safety limit value was a 2. So in the case of the reduction ratio, the reduction ratio should be less than 50%, or you can say 0.5. Then the third one, the third factor that is required to determine the feasibility of the drawing operation, that is a thickness to diameter ratio, that is T by D. We know thickness to die of the blank ratio, thickness to diameter ratio. So it is often expressed in percentage. It is desirable that the thickness to dB ratio should be greater than 1%. So it is desirable that the thickness to it is recommended that it should be greater than 1%. So as the thickness to diameter ratio decreases, and there is a possibility that the wrinkling will occur. Right, so if it is lower, so the wrinkling, there is a possibility that wrinkling will occur in the walls of the cup. So in cases where these limits on drawing ratio, reduction ratio and the thickness to diameter ratio are exceeded by the design of the drawn part, the blank must be drawn in two or more steps. So if, let's suppose, if we are performing, if we want such a product that these limit will exceed, so then we should perform that operation in multiple steps instead of single step. So as like in the case of the rolling and the case of the forging, like in the case of the rolling, we had the value, if you remember, that is known as the D max, that is the maximum draft. So that maximum draft was for the single step, that the maximum amount of reduction that is possible in the single step. So the same case here, these three factors are for the single step, that in a single step this dr shouldn't be less than 2, or in a single step of the drawing the R reduction ratio should be less than 0.5, or the thickness to diameter ratio should be greater than 1%. So if we are desiring such product which exceeds these limits, so we should perform that operation in the multiple steps. Then there's a blank size determination and blank force determination. So we will start with the blank force, or the drawing force. It is, you can say, the drawing force. The drawing force required to perform the given operation can be estimated by the formula pi dp, the diameter of the punch, into the tensile strength of the material, into the dv by dp. If you remember what it is, that is a drawing ratio minus 0.7, where this is in the force in Newton, and as you know, the T is the thickness of the blank. There is a T here as well. Let's make a correction. Into the thickness. So we have dp is equals to punch diameter, and T is the stock thickness, and T is the tensile strength, right? And dB is the blank diameter. There's another thing, that is the holding force. Obviously, as I said, we have discussed earlier that the holding force also plays a significant role in performing the drawing operation. So the F h would be equals to 0.015 y into the pi. That's into dB square, the die of the blank square, minus dB plus 2.2 of the stock thickness plus 2 RD. This is the value for the holding force that is to be exerted by the blank holder. So we have the Y is equal to the yield strength of the sheet metal. The Y is equal to yield strength of the sheet metal, and that is obviously in the megapascals. So the holding force, as an empirical observation, the holding force is usually 1/3 of the blank force, where FB is the blank force. So that's an empirical observation. So if we start with this numerical, a cup is to be drawn in a deep drawing operation. The height of the cup is 75 millimeter and its inside diameter is 100 millimeter. The sheet metal thickness is 2 millimeter. If the blank diameter is 225 millimeter, determine the drawing ratio, reduction ratio, thickness to diameter ratio, and does the operation seems feasible. As we know that these three parameters are used to determine the feasibility of the drawing operation. So let's write down the data. The height of the cup is 75 millimeter and its inside diameter, so it means the die of the punch is 100 millimeter. The sheet metal thickness is, that is the stock thickness, is 2 millimeter, and if the blank diameter is 225 millimeter, determine the drawing ratio. Determine the drawing ratio. And the thickness to diameter ratio, thickness to, as you know, it was the blank diameter ratio, and the reduction ratio as well. So we know that the dB is equals to 225 divided by the 100, and thickness is 2 millimeter divided by the thickness 225, and this one would be equals to 225 minus 100 divided by the 225 millimeter. So you can calculate for these values. So we have 225 divided by 100, so we have 2.25 value for the diameter ratio, drawing ratio, and for the thickness to diameter ratio we have 0.008%, 0.008%, or you can say 0.008 value, or it can be written as 0.8%, and this one would be equals to 225 minus 100 divided by 225. It is 0.55. So as we know, the upper limit of the drawing ratio was 2. So it should be less than or equals to 2, and in this case it is exceeding this value of the 2, and the thickness to diameter ratio should be greater than 1, but in this case it is 0.8, and it should be less than 0.5, and it is 0.55. So this operation is not feasible. So that is how we can calculate the feasibility of the drawing operation. There's one last topic that we had left, that is the blank size determination. As we know that for the final dimensions to be achieved on the cylindrical drawn shape, the correct blank size diameter is needed. So it must be large enough to supply sufficient metal to complete the cup or the drawing operation. And if there is too much material, this will result in the waste of the generation of the waste during the drawing operation. So we have to select some in between conditions for the perfect drawing operation to take place. And especially for the drawn shapes other than the cylindrical cups, the same problem of estimating the blank size exists. Only the shape of the blank may be other than round would be difficult. So there are some reasonable method for estimating the blank size or the diameter in a deep drawing operation that produces a round part, especially the cylindrical cups and some complex shapes. As we know that the volume of the final product is same as the starting sheet metal blank, then the blank diameter can be calculated by setting the initial blank volume to the final volume of the product. As we have repeated this as we have used this method in the previous deformation processes. So the initial blank volume is equals to the final blank volume. This is a simple method to calculate the size of the blank. Then the blank diameter can be calculated by setting this one and solving for diameter dp to facilitate the calculation. Right, and we while performing this one, we will assume negligible thinning. Negligible thinning of the parts. Right. So if you are given the initial diameter of the blank and the final diameter of the cup, you can say, and the height of the cup, right, and its thickness, so you can simply find out the initial size that is required, that is to be fed in the drawing operation. So that's all for this lecture. In the next lecture, we are going to see some specialized drawing operation that are used for some special purposes and using some special tooling. And then we'll move towards some other sheet metal operation that are performed from the metal and the rubber toolings. Assalamu alaikum.